Okay, thank you very much for the introduction, and also thank you for the invitation to speak today. I'd like to start with some acknowledgments and thank you to my collaborators and my group. So we have a group and also the XPD Beamline staff and some collaborators. I'll be mentioning them and their contributions throughout the talk. I'd also like to thank the DOE Office of Nuclear Energy for a Nuclear Energy Enabling Technology Award, which provided funding for this project, and also Brookhaven National Laboratory for LDRD funding. So today I'll be talking to you about using X-rays to study nuclear reactor pressure vessel steels and the implications of that to the energy supply of the United States. We'll also be talking about the really nice and wonderful modern new tools that we have at Brookhaven for material science and how automation is really crucial to enabling this technology for users from the nuclear materials community. Then I'll give 3 examples of using X-ray characterization of steels for our research and talk about some future work and future NSLS-2 beamlines. So nuclear energy provides 19% of the non-emitting energy in this country. So to generate electricity, almost 70% of our electricity is generated with fossil fuels. Nuclear is 19% of that, but it is an entire 63% of the non-emitting electricity generation in this country. And so by non-emitting, we mean very low CO2 emissions. So nuclear is crucial to meeting our carbon reduction goals. And most of the nuclear plants in the US are 40 years old. So keeping these plants safe and extending their life is key to providing this baseload power that we need to meet our carbon reduction goals. So the current plants must be operated for more than 60 years. If that doesn't happen, the amount of nuclear power will decrease very rapidly in this country. So today's reactors have significant problems with aging and material degradation. Nuclear reactors work by generating heat in the core. This is through the fission of uranium and plutonium in the core. The heat is removed from the core with water in the primary loop. So water takes the heat from the core to the steam generator. There's another loop where water moves from the steam generator through the turbines to generate electricity. So water from the primary loop that passes through the core does not pass through the containment structure outside. They're separate systems. And there are several barriers to fission product release in nuclear reactors. We'll discuss some of them in the core on the next slide, but I want to point out that a very important barrier is the reactor pressure vessel. So this is will be the subject of most of my presentation today. In addition to the reactor pressure vessel, another barrier for the release of radioactive materials is the outside containment structure, which is a concrete and steel wall that's 3 to 5 feet thick. So there's layers of barriers to the release of fission products, and we'll be discussing the core and the reactor pressure vessel. And all of these systems, the piping, the pressure vessel, the core, they're all subject to aging and material degradation. So significant challenges to life extension are related to material science. This shows a fuel assembly from a core. The fuel is located in small fuel pellets, the uranium dioxide, and these pellets are located in a fuel rod, which is clad, which is known as cladding. So currently the cladding is zirconium alloys, but there's also efforts to replace the cladding with advanced materials and advanced steels. According to the Nuclear Regulatory Commission, The top 3 challenges for life extension are irradiation-assisted stress corrosion cracking, reactor pressure vessel embrittlement, and primary water stress corrosion cracking. I mentioned the stress corrosion cracking because I'll return to those later in the presentation, but just to describe how this process and how this phenomenon occurs, it's a combination of corrosion and stress being applied to the material simultaneously. So the material's in an environment that causes corrosion, a corrosion film forms, and then the material is stressed. When you apply that stress, it breaks the corrosion film and exposes bare material beneath. And then that material corrodes. And of course, you apply more stress, and so the process continues, and you get this slow, stable crack growth that's very damaging over time to the materials in a reactor. The materials used in the reactor were designed 40 years ago using the very best technology and material science that they had at the time. But there's been many advances in material science since then, and of course in the characterization tools that we have. So one of the goals of our research is really to apply these modern material science tools to develop a better understanding and performance prediction for these aging materials. Nuclear reactors pressure vessels suffer from radiation damage. So this shows a pressure vessel. They're enormous structures, 500 tons, 14 meters high, 20 centimeters thick. And during their life, they're exposed to neutron irradiation, which changes the material properties over time. So at the beginning of life, you've carefully designed your material and built it to within specification, and you have a certain material. Over time, the microstructure of the material changes. So 20 years, 40 years, 60 years, you no longer have the same material that you started with at the beginning of life. And how this material changes through time depends on many factors. In steels, it depends on the chemistry, so there's many alloying elements in steels. In addition, it depends on the product form. So we know that copper causes an increase in the aging rate, and we know that welds have more copper than, say, forging. So the product form is also important, and also the conditions where the radiation occurs. So under normal operating conditions, the temperature of the reactor pressure vessel is around 290 degrees C. But that temperature can vary slightly, and the variations in the temperature also affects the amount of aging. In addition, there's the amount of energy in the neutrons and the number of neutrons. So we've talked a lot about how neutron radiation can cause damage in materials, and this is a movie that will demonstrate the type of damage that is caused. So in a material, the atoms in a metal like to remain in certain positions. And radiation damage occurs when these atoms are hit by an energetic particle and knocked off the position. Many of them will be removed from the position. They'll wiggle around, and most of them will come back, but still defects are created. So this movie shows an example of an energetic particle causing what's known as a displacement cascade. In this case, it's xenon. You can see it starts to displace atoms. As time goes on, displaces more and more atoms from their sites. You can see the time scale of this is in picoseconds. So the atoms are returning to their equilibrium positions. And now at 100 picoseconds, many of the atoms have returned to their equilibrium positions, but defects have been created. So some defects remain in the material. Not all of the atoms are able to return to their initial positions. And in steel, this causes the clustering of alloying elements. So you get clusters of the alloying elements in the steel, and these are known as nanoprecipitates. So this graph shows the type of radiation damage that you can get in materials versus a radiation temperature relative to the melting temperature of the material. So we're down here. We're at relatively low temperature relative to the melting temperature of steel, and at fairly low This is a measure of the number of neutrons. So there's fairly low number of neutrons because the pressure vessel is actually some distance from the core. So we're here, and we see radiation embrittlement, which is caused by the formation of the nanoprecipitate. However, at higher temperatures, you can get additional types of damage. So you can see voids, solid segregation, and void swelling. You can actually get cavities on the grain boundaries that causes macroscopic swelling of the material. So all of these areas and all of these types of radiation damage are things that have the potential to be studied with X-rays. So this chart shows the type of radiation damage that occurs in materials. This is the time scale of the damage, and this is the length scale of the damage. So the movie I just showed, we were down here. We were looking at atomic. The length scale was on the order of the atoms, and the time scale was picoseconds. And then our embrittlement phenomenon with reactor pressure vessels is up here, because we want to look at a structure that's 20 centimeters thick, and we want it to last 8 decades. So we span an enormous number of time scales and length scales with these types of material science problems. And our community has a good understanding of what's going on in this time and length scales from simulations and from the movie similar to the one that we just saw. We also have engineering models to predict the performance of our materials at these long time scales and length scales. Where we struggle the most is this mesoscale region and the evolution of defects after they're created, how they evolve with time, and how the microstructure changes with time. And this is really this is sort of the sweet spot for the synchrotron and for looking at materials with X-rays. So in the past, nuclear materials were really limited at synchrotrons because of limits on radioactivity. And one of our goals is to really increase access to the synchrotron for radioactive materials so that we can apply these tools to material problems in this region. So steel has a complex microstructure, and I'll be discussing this in some future slides. So I just wanted to introduce the concept of the crystal phase. So crystal phase and the lattice is just the way the geometric arrangement of the atoms in space. So this is a body-centered cubic arrangement. This is a face-centered cubic arrangement. And this is what I'm referring to when I talk about the phases of the material and the lattice. And there's additional phases that we'll also be discussing today. But these are called unit cells for the material. These unit cells assemble into a grain structure in the material. And these large, these relatively large collections of atoms are known as grains. So this is the bainite microstructure, which is a steel that's commonly used for pressure vessels. So I'd like to now describe why the damage is so severe to pressure vessels. So fracture depends on the ductility of the material. The mode of fracture in a material depends on the ductility. And this is controlled by line defects in the material known as dislocations. So you can see a dislocation here. It's an extra line of atoms in the material. And this allows the material above and below to slide past each other. So this allows the material to deform. This is a deformation mechanism in the material, and this is a good thing in steel. Because what you want is you want the material to deform before it breaks. And with ductile failure, when the material is able to deform, you'll get a large amount of deformation, and you'll see necking before it breaks. And this type of deformation can also occur like in front of a crack tip, blunting the crack tip. But in ductile fracture, this is a stress-strain curve, And you can see how much more energy, the area under the curve is the absorbed energy. So for ductile fracture, you absorb a lot more energy before you fail. Now, if these dislocations can't move for some reason, and if there's, say, a large nanoprecipitate that prevents the movement of the dislocation, the material can fail in a brittle way. So in this case, it just snaps. And so we absorb much less energy, and the failure happens much more quickly. So we have the material is just less tough. And this phenomenon also happens at low temperature. So at low temperature, the dislocation motion is also impeded. So it can be impeded by low temperature or nanoprecipitates blocking dislocation motion. This chart shows the fracture energy for pressure vessel steels versus temperature. So the blue graph is new reactor pressure vessel steel. And you can see down here, this is brittle failure, but you can see it's happening at minus 100 degrees Celsius. So this is not really a temperature regime where you would ever see with a reactor pressure vessel. So you don't have to worry about brittle failure in new material. Then it transitions, the material becomes harder and harder to break it until you get to your completely ductile failure. After you irradiate the material, you shift this temperature where this change to brittle failure occurs to a much higher temperature. And now you have to worry about brittle failure at temperatures around over 100 degrees C, 150 degrees C. And so this starts to impact your operations and how you're able to run the plant and run the reactor. And in addition, you've lost a great deal of what they call upper shelf toughness. So your final toughness, even at high temperatures, is much less than it was when you started operating your plant. So when you started operating your plant, you didn't really have to worry about brittle fracture. Now all of a sudden, it's something that you have to consider. So these curves are based on what's known as the Sharpie test. And they take a coupon of material. This sample is a coupon. It's about 10 millimeters by 50 millimeters. And they just hit it with a hammer. It already has a notch in it. And they measure how much energy it takes to fracture. And they do that over and over again. And then they draw the curve. So there's already samples of this type that have been looked at and irradiated and measured to draw these curves. In fact, this has been a problem, a known problem for many years. So there are literally thousands of samples of irradiated steel that we can use to study the effects of chemistry, product form, and irradiation conditions. And again, the reason you need so many samples is because there are so many factors and they're interrelated. So to try to unravel that and determine what's really impacting the aging of the material, you need many, many samples. These samples come from the Power Reactor Embrittlement database. These are actual surveillance coupons that are similar to what we saw in the previous screen that hang inside nuclear reactors and are irradiated at the same rate as the pressure vessel. And every once in a while, they take them out and fracture them. And then there's also controlled programs. So the irradiation variable program where they make various model alloys where they vary the chemistry, and then they irradiate these in test reactors around the country at different dose rates and temperatures to also simulate these conditions. Now, the challenge is that for the irradiation variable program, where you're irradiating things in test reactors, you're doing it at a much higher rate. You're putting many more neutrons in it more quickly than it would see in operation. So then you have the question, is the material representative of real material coming from a plant? And of course, you don't have real material coming from a plant that's been in operation for 60 years or 80 years because the plants obviously aren't that old. So the idea is to move to a better understanding and more confidence in our predictions of the phenomenon. So there's very little data on the long-term exposures that are crucial for life extension. And we're really trying to improve our understanding in that regime so that we can better inform the decision on reactor pressure vessels. These experiments are conducted, many of them at the Advanced Test Reactor at Idaho National Laboratory. So our collaborator right now, Robert Odette at the University of California at Santa Barbara, has over 1,600 samples coming out of the ATR of various model alloys. These samples take a very long time to produce, and they're extremely expensive. So for a year, you might design the experiment, then they're in the reactor for a year, then they come out of the reactor, they have to cool down for a year or two, and then they are characterized. So an entire experiment could easily take 5 years. We want to perform additional characterization on the materials to really get as much information as we can from all these samples that are available. And Brookhaven, of course, has the perfect new tool to do that. This is the National Synchrotron Light Source 2 at Brookhaven. So now we have a problem that can impact the electricity supply for the United States. We have a large number of samples available to study that problem, and at Brookhaven, we have the perfect tool to characterize the microstructure. At this point, I'd like to discuss our first light experiment at the NSLS2 and how we are working to enable access to the synchrotron for users with radioactive materials, and the fact that automation will be crucial for those efforts. So NSLS2 had a first light experiment on brittle fracture in reactor pressure vessels. The first goal was to improve the understanding and modeling of the pressure vessel steels. The second goal, and this was a distinct goal from the DOE, so the characterization goal was actually part of what the DOE was looking for from this work. It's to develop an automated system to rapidly acquire data on radioactive materials. So we developed a sample holder and a sample magazine that can be used with a robot at the XPD beamline, and we've also been working on automating the data analysis for the large data sets that we'll get from using the robot. So just to summarize quickly the phenomenon, the potential for brittle fracture could impact life extension for current reactors. It's caused by nanoprecipitates. They embrittle the material by preventing the motion of dislocation. We need to understand the role of chemistry and environmental conditions on the formation of these nanoprecipitates, and we want to use advanced X-ray techniques to do that. We want to use advanced X-ray techniques to tell us more about the nanoprecipitates so that we can understand the phenomenon. So this models already exist to estimate the change in the RPV fracture energy from the microstructure of the material. So we have radiation damage, which leads to the formation of the nanoprecipitates, which leads to an increase in the yield strength in the material. And in this case, an increase in the yield strength in the material is a bad thing because it limits the ductility and pushes the material towards brittle failure. And from this increase in the yield strength, we're able to predict a change in the energy to fracture. So the theory, the model that we have, says the increase in the yield stress is based on the volume fraction and the radius. We need information on the volume fraction and the radius of the nanoprecipitates to estimate the yield strength. So these dots are representative of the nanoprecipitates, and this is the dislocation. So as the dislocation approaches the nanoprecipitates, it has to bow around the precipitates. And some of them can be cut, some of it has to bow, because these features can be of different strength. But we must, in order to apply the theory, we need data on the volume fraction and the radius of the nanoprecipitates. This is the X-ray powder diffraction beamline, and I'd like to thank Eric Dorhe and Sanjit Ghosh for their assistance in our first light experiment. The X-ray beam comes from here. Our sample is placed here, and the detector is here. There's also a robot at the beamline. The robot can pick samples up and place them in the beam. And some of the other features that are essential about XPD for our work is the energy range. So since it's a high energy beamline, we're able to look right through our steel samples. So we look at the samples in transmission geometry. The X-ray beam passes completely through our sample. Also, the spatial resolution. It has a fairly large spot size, so we're able to sample a lot of the material at once. We're able to see many grains of the material at the same time, which is also important. And of course, it has extremely high flux. So it's, each of the measurements is very short. And that also enables the high throughput, and it really makes sense to have a robot at this type of beamline. And these, the RPV steels were a first light experiment in February. So this movie shows the robot working at the XPD beamline. See, that's the sample magazine that just opened up. The robot reaches down. These are capillary sample holders, picks up a sample. It's rotating now. There's a camera at the base of the robot that can read a barcode on the sample holder. So the robot rotates the sample in front of the camera and then places it on the diffractometer. Then it returns to a neutral position. So this is extremely fast. And after you've taken the measurement, the robot will return the sample to the sample magazine. So this is an extremely fast process. To give you an example, to take this data at X17 at the NSLS took 15 to 30 minutes per sample. At XPD, it would take much less than 3 minutes, and that was at a fairly low current. When the current is higher, this time will be even less. So that's great. And of course, we're able to get the high throughput for better statistics, and also unmanned operations. These are the sample holders that we designed for radioactive materials. This is one of our samples. This is a sample of reactor pressure vessel steel. It's only 2.5 millimeters at the maximum, and it's just about a millimeter thick. So our users have to wrap the sample in this orange tape. It's about the consistency of Scotch tape. You wrap the sample in one layer of Kapton tape and then stick it to a plastic ring. And then they can ship the ring to us with the sample in it. We put it on the base and put the ring, it has a magnetic closure to reduce loading time. And then when we want to remove the sample, there's a post that lifts the sample and lifts the magnet off. So the sample holder provides containment, and all the samples at the light source require at least a single level of containment. So none of the samples are loaded or unloaded at the light source. These are the sample magazines. These can be used at the beamline. So this is our sample magazine for radioactive materials. It's magenta and yellow, the colors for that. And this shows a sample loaded in the base. So these sample magazines could hold up to 20 samples depending on the amount of radioactivity. Or they could, if the samples were more highly radioactive, you could just have one sample in each of the magazines. and you could ship the magazines back and forth to the users. Or for our first light experiment, since we had 180 samples for our first light experiment, so we just sent the plastic rings back and forth, and they were all very low level. Now I'd like to give 3 examples of how we were able to use X-ray characterization on these steels. And I'd really like to thank David Sprouster for his great contribution to the data analysis on these experiments. This is the first example. We did small angle X-ray scattering at XPD just in April as our first light experiment. So we have an incident X-ray beam. It hits the sample. These are the nanoprecipitates, scatters off the nanoprecipitates, and this is the image that we collect at the detector. So this is the image from the detector. So then we take the integrated intensity from this image and plot it versus the scattering vector and fit a model to it. Okay, now I'm going to switch to the next slide, but this image is going to be repeated. So here's the same image, and from this fit to the model, we're able to extract the volume fraction and the diameter of the nanoprecipitates in each of the samples. So now we have a list of our samples. So in our case, we would have 180 samples. We also have the size and the volume fraction of the nanoprecipitates. So at this point, we've met the goal of the experiment. We have provided characterization on the microstructure that fits with the theoretical model we have for embrittlement. So we're able to contribute to the theory and the understanding of reactor pressure vessel steels embrittlement with just these very straightforward results from our first light experiment. Now, my second example, I'd also like to talk about some of the new science that's coming out of these experiments. This is X-ray diffraction data that we took on the model RPV alloys. So these peaks are diffraction peaks, and they're sort of a fingerprint for the crystal structure of the material that I showed you earlier. So by identifying these peaks and matching them with known peaks, we're able to identify the phases in the material. The red line is unirradiated material, and the blue is irradiated material. So in this case, in the red, we had 3 major phases. We saw ferrite, austenite, and cementite. We were able to fit a model to the data and determine the volume fraction of the phases and get the grain size. Then we also did the same thing with the irradiated material. With the irradiated material, we see that one of the phases, the austenite, greatly decreases. The amount of it decreases after irradiation. The cementite grain decreases also. And the iron matrix indicates that defects have been formed. We also see quite a large change in the background. So these curves have not been offset from each other. This difference in the background is real. What we don't see is our peaks from the nanoprecipitates. So we don't see a fingerprint in these patterns from the nanoprecipitates, and that's really what we were looking for here. I mean, these changes in the microstructure are very significant for the aging of the materials, but we really wanted to identify the nanoprecipitates. So why are these nanoprecipitates so difficult to see with X-ray diffraction? We know they're there, right? We measured them with SACs. I showed that in the first example. And we also have transmission electron microscopy of the nanoprecipitates, so we can see them in microscopy. So why don't we see them with diffraction? Is it because there's just not enough of them? Well, according to our SACs measurements, there's 1 to 3%, and that should be enough to see with high-resolution X-ray diffraction. But they are very, very small. They're 2.5 to 4.5 nanometers. And for these types of materials, they have a relatively large unit cell. The unit cell is 11 angstroms. So some of the precipitates might only be a couple of unit cells in size. And that means that there can be size effects. So those nice cubic structures and the crystal structure may be distorted just because of the small size. And that can occur strictly because of the size or also because the interaction between the particles and the surrounding matrix. So to further look into this, we use the information that we have from other techniques to inform the models that we created. Now in this graph, again, the red is our data, that's our observed data, and there's no unirradiated data on here. This is all irradiated. So we have the red is the irradiated material, the blue is our model that we fit to that data. Now the model is a combination of the phases that we identified in the material. So we have our BCC iron, our FCC iron, we have our cementite, and then we also added, this is the nanoprecipitate phase. And this is this blue line. So you can see the blue line, due to the small size, has these very small, broad peaks. There's no sharp peaks from it, but it does contribute to the background, and it does have peaks. So this model, by including the nanoprecipitates, is a much better fit to the data than it is without including the nanoprecipitates. So in the model, we fixed the size of the nanoprecipitates based on our SACS results and the transmission electron microscopy. We refined the unit cell, so it returned a reasonable unit cell. It returned a reasonable volume fraction, and we were able to identify the phases of the nanoprecipitates. And this is an extremely significant result because the phase that we predict agrees with the thermodynamic models. So we were able to lend a great deal of support to the idea that the nanoprecipitates are crystalline. They're not just random clusters of atoms in the material, they're actually crystalline. And this means that they're thermodynamically stable and that they will persist over time in the reactor. So once you've created them, they will persist. So this is the last example that I'll show. And this is an example of how we'll be using automation of data analysis to increase the amount of throughput and what the implications of being able to do that are on our system. So this is the 2D diffraction pattern that you collect at the detector. This is then integrated. This is, again, these peaks are the fingerprint of the material. And we do a phase ID, and then we fit the pattern. From the fitted pattern, we are able to get the crystal phases, the size of the unit cell, the size of those lattice parameters, and also the strain. So with batch processing, our users will leave with this information, which is what they really want. So they won't just be leaving with these images from the detector, they'll actually be leaving with the information that they need for their scientific models and theories. And for us, this means that we can use the large amounts of data that we have to reduce the uncertainty in the performance predictions and also to predict interactions between those many variables that we outlined at the beginning. So we'll be able to predict the combined effects of chemistry, product form, and irradiation variables on the response of the material. So this will allow us to really improve the predictions and understanding of the performance and to optimize the microstructure and the conditions for the operating conditions. So we'll also be able to inform them on what would be an optimum microstructure for new materials. Okay, and finally I'd like to talk about some of the future work that we have ongoing at the Synchrotron, and also a proposal that we have for a future NSLS2 beamline. We'll go back right now very quickly. This was, again, the fuel assembly with the cladding. I'd like to mention my colleagues Simranjeet Gill and Mohammed Al-Bakhshwan. They've been working very hard on this. This is an in situ cell for studying corrosion at the light source. So this is a heater, and inside there's a small chamber. We're able to take a small piece of this cladding material, put it in the chamber. The chamber has windows that are transparent to X-rays, and we can watch the very initial and early stages of corrosion. This cell is capable of reaching 400 degrees C and providing a corrosion in a steam environment. We've already looked at some zirconium alloys and advanced steels. And with this, we'll be able to do real-time monitoring of the formation of corrosion films. Here's some other examples of materials that we've been looking at the Synchrotron. This is some work we've been doing with Idaho National Laboratory on low fluence irradiations of uranium molybdenum metallic fuels. This is a metallic fuel that is used in research reactors. So we've been doing X-ray diffraction on this material also. We'd like to do that at XPD. We've also been doing some tomography and imaging of in situ compression tests of silicon carbide composites. This is some work we've been doing with General Atomics. And silicon carbide has the potential to operate at much higher temperatures than the other cladding materials that we've discussed. So for new reactors, it could potentially operate at much higher temperatures and provide greater efficiencies. So it's a very important material. However, it does fracture. So they're trying to improve the microstructure to increase the toughness and to really provide the barrier to fission product release. So we're able to, the sample is in here. There's a load cell, and we put the sample under compression at the beamline and watch the crack grow, take images of it. I discussed the in situ corrosion testing of the clad. We've also been looking at irradiated samples of other types of materials that could be used for cladding. And these are mainly the advanced steels. And we're doing very similar experiments to the steel that I described for the reactor pressure vessel. We're looking for defects created in the material from the damage. We'd like to do that with XRD and SACs at the XPD beamline. And then as a final example, I'll mention that we looked at the in situ absorption of fission gas. So during the fissioning process, fission gas, largely xenon and krypton, is generated, and this can build up and pressurize the inside of the cladding. So absorbing that could potentially reduce the pressure and allow for higher burnups in the fuel. We used a metal organic framework to try to absorb xenon. We were able to perform an in situ experiment where we put the metal organic framework here and flowed the xenon past at the light source. And by combining the diffraction results with computational studies, we were able to determine the sites in the metal organic framework where the xenon was being absorbed. Also part of our future work is to establish a partnership with the nuclear science user facilities. The nuclear science user facilities is a national collection of facilities and instruments with the goal of advancing nuclear energy science and technology. So this consists of the advanced test reactor that I showed you earlier at Idaho National Laboratory and other test reactors around the country, such as the one at MIT. It includes other irradiation facilities, such as ion beam facilities at places such as University of Michigan and University of Wisconsin. And it also includes characterization facilities. So for example, Idaho National Lab has a new characterization facility known as the Irradiated Materials Characterization Laboratory. And this is really a suite of microscopes and instruments that's very similar to what would be provided at the Center for Functional Nanomaterial. And by forming this partnership between the NSLS2 and the NSF, we will be able to leverage a research model that's similar to the one for the NSLS2 and CFN, only for radioactive materials. So for these materials, we would do the microscopy at the IMCL in Idaho, and then do the X-ray studies at the National Synchrotron Light Source 2. So this partnership is very important to establish greater access to the synchrotron for all the users of these other facilities. And finally, I'd like to conclude with a discussion of our proposal for a future beamline at the NSLS2 for studies of, in situ studies of materials in a radiation environment. And this is a proposal for a beamline that's located in a separate facility outside of the ring. So this is the NSLS2. This is a beam pipe that would transport the X-rays to a separate facility. And I want to point out that this is a conceptual design. This is a proposal. And this beamline would provide two unique capabilities. The first is that it would allow the characterization of more highly radioactive materials than is currently allowed at US synchrotrons. The second is that it would allow for the in situ studies of radiation damage with particle beams from multiple accelerators. So this is a schematic of the end station with particle beam accelerators. So here's our sample. And in this case, we bombard our sample with either self-ions or protons to create the radiation damage. Simultaneously, we also use helium. And while we're doing that, while we're creating the damage, we probe the material with X-rays and watch the damage evolve. So this could provide, this facility would be unique in the world, and it would provide new understanding of how the microstructures develop over time under radiation damage. At this beamline, we would have diffraction and spectroscopy, and an energy range of between 7 and 35 keV. Again, we would use self-ions or possibly protons to create the damage, and we would be able to look at structural materials such as the cladding that we've discussed, waste forms for nuclear waste, and materials for radiation-hardened electronics. And then finally, we're also proposing an end station with the capacity to handle more highly radioactive materials than are currently allowed at US synchrotrons. This would provide diffraction and imaging at high energy range for studying materials such as spent nuclear fuels and dispersible radioactive materials. So this would really allow us to apply the most modern tools available to material scientists to materials for nuclear energy systems. And it could really change the way nuclear materials development is performed and how, and our understanding of the materials that we use today. Okay, thank you. Any questions?
Can we have time for some questions?
You're looking at very, very small pieces of material, and yet you say a vessel and very, very large. How homogeneous is this clustering or damage in these materials? In other words, what you study being very small, is that reliable when you extend it to an entire structure?
you bring up a very good point, right? That's almost like another variable. So the reactor pressure vessel is enormous, right? Most of the radiation damage is going to occur in the beltline region of the vessel. So that's the region adjacent to the core where the neutrons are coming out. And then in addition to that, right, the vessel can be 20 centimeters thick. So the material closest to the core is going to experience more damage than the material farther away. So that's another set of variables. So you have to understand the performance of the material throughout the entire structure, and you need to incorporate that into your engineering scale models.
What are the most common transmutation materials that are produced in these reactor vessels? We have neutrons, and presumably we're transmuting these steels into something which slowly changes with time, as you mentioned. I'm just curious as to what are these materials that are being created?
There's a lot of, say cobalt and some radioactive rare earths. So in the samples that we have, most of the radiation that's coming off is beta. And even though some of the samples have been quite high, when you wrap them in Kapton tape, it really reduces the amount of beta radiation coming off, and we're able to handle them at the light source. Oh yes, yes, they do take a direct interest in this. This project was funded by the DOE, but I do think industry takes a direct interest. Or I mean, this research was funded by the DOE, but the NRC and.
Even though there's no market for reactors in the US right now?
Yeah, there's a lot of research going on into small modular reactors, and there's several companies that are developing new reactor designs. So they definitely have an interest in new materials and improved materials. And even for companies such as TerraPower, when they go to, I mean, they're entirely new reactor designs, but some of the steels that they're looking at are, say, HT9, which was irradiated many years ago in some of these test programs. So even the historical materials are still of great interest because we do have some data on them. So they put some effort into finding a vendor who would make additional heats of HT9.
You mentioned that the nanostructures formed from the radiation damage. As a result of your experiments, you found that they are themselves characterized by a crystal structure and they are stable. Is there a typical structure that you have found, and is it influenced by the chemistry, the temperature, or by some other variable as to what gets formed?
As to what gets formed? Certainly, yes. There are actually two possible phases for the precipitates that we've been looking at based on the composition. So based on the composition of the steel, you get different composition in the precipitates, which gives you different crystal phases that are predicted by the thermodynamic models. And our models with the fits to our data are showing that those same phases are selected for these chemistries. So we're predicting the same phases, even though there's more than one. We do predict the same phases as the thermodynamic models do. So while these nanoprecipitates, they may be thermodynamically stable, but they are still getting irradiated with neutrons. So they can dissolve just from radiation, from additional radiation damage.
Okay, if there are no other questions, we'd like to invite you to join us.
Okay. Thank you.